No, we see the presenter view. So you, yeah,
Oh, yeah. So this is the problem. Yeah, there we go. Now do you see it now?
yeah.
Okay, yeah, that's, we've got two screens going. Let me see. I'm going to see if I can get a laser pointer too. Oh, no. Okay, let me move this. Good. Okay, so I'm going to try to tell you about topological insulators and what they are, and how we think that they can help us save the world. So let me see. There we go. Okay, so let me tell you about the challenge that we face that we're trying to solve. And the question is really, is the information technology revolution something that's sustainable? So what do I mean by information technology revolution? Well, you know, these days everybody actually has a little supercomputer in their pocket that they carry around with them, and you know we have these really fantastic devices. They do all kinds of things for us. We use them, you know, we expect them to predict the weather, you know, do all kinds of sound and image and video processing, you know, predict our route through traffic, and you know, how to optimize it. And you know, we want them to do lots of things in the future. You know, I'd particularly like it if I had good real-time speech translation. Actually, you can get this now, so it's something that you can do, works okay. You know, we want our computers to drive our cars. We'd like, you know, particularly these days where we can't travel anywhere, it'd be fantastic if we could have meetings in really good immersive virtual reality, so that, you know, it was just like we were actually in the same room with somebody, right? So there are things that we could do that we can't do now that we'd like to do in the future. So a lot of this computing actually these days doesn't take place on our device. It takes place in the cloud somewhere, which actually physically means it's in a server farm somewhere. And those server farms use enormous amounts of electricity. And if you're in Australia, you know, our local power plant is coal-fired, which is unfortunate. But we have a lot of coal, and they tend to just dig it out of the ground. You can see actually there's a big pit next to this one. They just dig it out of the ground, dump it in the power plant, and make electricity. So that's bad. IT, actually, information technology as a whole, consumes about 8% of the electricity on the planet. And it's growing more rapidly than any other sector. So it's more CO2 emissions right now than air travel. Well, a lot more, because nobody's traveling by air anymore, but it was last year. And so it's a growing problem. And, you know, eventually we have to do something about it if we want to, you know, keep having these gains in computing. So computing is all done with transistors. This is the basic unit of computing. You know, transistors are little electronic switches. We're really good, and when I say we, I mean the human race. We're very good at building transistors, probably better than anything else. So we've made 3 × 10⁻21 transistors, approximately, very approximately, in all of history, and of course most in the last couple of years, because the number grows exponentially. That's far more than the number of grains of sand on Earth. And it's amazing. I mean, our ability to make transistors has kept up with this huge demand for computation. The number of computations that we perform every year grows by about 70%. And this has been true for about 40 years, which is incredible that something can grow at 70% a year for 40 years. And that has been possible because of this thing called Moore's Law, the fact that we latched onto a technology that allowed us to have these incremental advances every year to make the computer chips just a little bit better, a little bit faster, more transistors. We could double the number of transistors on a chip every 2 years, and that actually made them smaller, and they made them more energy efficient. So they got about 40% more energy efficient every year. And those numbers roughly cancel, right? So if you get 70% more computations that are 40% more efficient, it's like 1.7 × 0.6, so it's about 1, right? So, but the problem is that this Moore's Law is ending. This ability to keep making transistors smaller and smaller and faster and more energy efficient is kind of coming to an end. So some of these things have already come to an end. Computer chips no longer get faster. And so, in fact, you know, this is an interesting graph, as it's actually economic in nature, not technological. There's this little inset here that says transistors bought per dollar. It used to be that the real reason that people made more transistors on a chip is that you could actually, it was more expensive to make the chip, but less expensive per transistor. And so there's an economic advantage, and that is actually running out. And so it's really not clear exactly when this is going to completely lose steam, but probably in the, you know, right around now or in the next few years, it seems like we're going to stop being able to make better, more efficient computer chips every year. So if we want to keep having all these gains of computation, which we think are actually good for us and good for, you know, they have benefits to society, they make a lot of things more efficient. We need some new energy efficient computing technology. We need to do something actually completely different. We don't know what that is. So this is a good thing for physicists. It means that there's a sort of a basic challenge, basic science challenge here. You know, how do we make something that's more energy efficient than the current silicon CMOS computing technology? So that's what our center is about. It's called FLEET, Future Low Energy Electronics Technologies. And we're really focused on classical computing, not quantum computing, but really just, you know, regular old computing, transistors. And we want to make those transistors switch at with lower energy, which means lower voltage. And we have a few ways that we're tackling that. And one of them I'm going to talk about today, which is this topological materials. We're also looking at exciton superfluids. This is a completely different thing. And using light or time-dependent electric fields to transform materials, and so, but which I also won't talk about. Okay, so topological materials. It's going to be the topic of the rest of the talk. So I'm going to try to explain what topological materials are. You know, some of you probably haven't had solid state physics, and some of you may have but haven't thought too much about it, you know. But when we talk about materials, there's sort of two basic classes of materials. You can divide materials into metals. Those are things that conduct electricity, and insulators that don't. Probably if you ask somebody who's in high school, or, you know, somebody who's not a physicist, you know, what's the difference? They'll say, well, it's chemistry. You know, some things, some elements are sort of naturally metallic, and some elements are kind of not metals. You know, and that explains a lot of what's going on, but it doesn't really sort of explain the microscopics of it, right? And it fails. That picture really fails for certain elements. You know, for example, carbon. Carbon has a couple of allotropes. You can make graphite, which is the stuff that's in pencil leads. Graphite's actually a metal. It conducts electricity. Diamond is a good insulator, so it doesn't conduct electricity, but they're both made of carbon. So there's nothing particularly, you know, unique to carbon in that it's definitely a metal or definitely an insulator. Tin is another example. So there are two forms of tin. There's white tin and gray tin. They differ subtly in the way that the tin atoms are put together. One of them is a conductor, a metal, and the other one's an insulator. So, so in order to really understand this, I think there's actually kind of one of the triumphs of quantum mechanics is understanding why some things are metals and some things are insulators. I don't think people often appreciate that that's a quantum mechanical property, but it is. So I'll kind of go through why that comes about. So what I'm going to plot here on the left is the energy of an electron versus its wave vector or its momentum. So, you know, kinetic energy is p squared, you know, momentum squared over twice the mass. And so this would be a parabola for a free electron. So if I take that electron and I put it in a solid, things get modified a little bit. So what happens in a solid is that we have a periodic arrangement of atoms in the solid. So what that periodic arrangement of atoms does is it makes some wavelengths particularly special, right? So there's some wavelengths and therefore some momenta that are special. And it modifies this, this dispersion relation. In particular, we actually find these gaps. And these gaps come about at these special wavelengths. And those special wavelengths are the ones that are commensurate with this lattice. And so what's going on is that at this gap, we can take two traveling waves, this one at negative wave vector and this one a positive wave vector, and we can make two standing waves. And those standing waves we could make in two ways. We can make one where the maxima of the waves overlap the ion cores, and so that's energetically favorable. The electrons want to stay near the ions, and so it'll have lower energy. And then this one, the maxima don't overlap the ions, and so it'll be raised in energy. And so you naturally get a gap here, and that's just because you took the electron and you stuck it in this periodic lattice. And those gaps are really important. You know, they're purely quantum mechanical phenomenon, but they lead to this behavior that, you know, once you need another quantum mechanical phenomenon, which is the Pauli exclusion principle. Every state you can only put two electrons in, one spin up and one spin down. And once you do that, you start filling up these states from the bottom, these allowed states for electrons. And if you've got one electron per atom, for example, then you actually get a half-full band. It takes two electrons to fill up the whole band. And so you'll get a Fermi energy, or the maximum energy for the electrons, which is somewhere in the middle of the band. And if you have two electrons per atom, you'll get an insulator. So you'll fill up one band completely, and then you'll have a gap in energy to the next allowed state. So why is one a metal and one an insulator? Well, you imagine applying an electric field. You apply an electric field, you can, in this case, in the metal, you can adiabatically shift these states to higher momenta on plus K, and that empties out states at lower momenta over here at minus K. And so you've got more plus K states than minus K states, and so this is a current carrying state. The electrons are going in one direction. In the insulator, there's nothing you can do. These states are all filled, so there's no low energy process that's going to move, that's going to cause an occupation that would carry current. So there's always just as many plus K and minus K states that are filled. And so even though each individual electron in this insulator is actually moving in a sense, it has some, you know, finite momentum, it's always balanced by some electron moving the other way. And so you'd have to promote electrons over this energy gap to give them some extra energy to make them move. And so this thing doesn't conduct. All right. So that was the end of the story in, you know, the 1930s, and it was the end of the story for a long time, you know, maybe 50 years or so. And then, so I'm going to tell you about a different kind of electronic system, which is you take take electrons and confine them to two dimensions and put them in a really strong magnetic field, and it'll become clear why in a minute. So electrons in a magnetic field are going to follow curved trajectories, and if you make that field really strong, the electrons will actually loop back on themselves before they scatter or somehow get you know, randomized or disordered. And so those little loops that electrons will make in a magnetic field, quantum mechanically, we can describe them by harmonic oscillators. So if you solve this, you know, Hamiltonian for electrons in a strong field, you'll find that the solutions are harmonic oscillator solutions. So they're localized in space, and then they're highly degenerate in energy. And you actually get this ladder of harmonic oscillator energy levels, you know, evenly spaced, as you would for a harmonic oscillator. So you can ask, is this system a metal or is it an insulator? Well, you know, you'd expect it's got an energy gap, you know, this gap that's given by this, you know, harmonic oscillator energy, the cyclotron frequency. So if you put the Fermi energy in that gap, you know, if you filled up all the states, all these Landau levels up to some particular energy, and then the Fermi energy was in a gap, you'd expect this thing looks like an insulator. Well, so actually nobody knew what would happen, but then the experiment was done. So this was a case where experiment preceded theory. And And the first experiments were actually done in semiconductors where the electrons were confined in 2D in a very strong magnetic field. And the data looks something like this. So the bottom graph here is the resistance. The top graph is the Hall resistance. So it's the Hall effect. And on the bottom graph, the horizontal axis is magnetic field. And on the bottom graph, you can see that the resistance is finite at low magnetic field. It doesn't do much. It's flat. And then it starts to oscillate at some point. And those oscillations are due to the fact that these spacing between these Landau levels is growing, and they're passing through the Fermi energy. And eventually those oscillations actually grow and the resistance goes to zero in between oscillations. So these are truly zero resistance states. There's no resistance, no dissipation in the sample at all. And those states actually correspond to where you have the Fermi energy in this gap. At those states, you actually get a quantized Hall conductivity or Hall resistivity. And so you have a plateau in the Hall resistance. So this is interesting. We expected an insulator, and we got something that conducts perfectly. So it's like the opposite of what you would expect. The resistivity and conductivity tensors have a very funny form in this state. And in fact, on these plateaus or these zeros of resistance, the resistivity and conductivity tensors only have fundamental constants in them and this integer nu. So that nu is an integer and it's exact to part per billion as far as we can tell. So there's no materials parameters at all in this. It's just fundamental constants. So this we expected it to be an insulator, but it's a very, very strange insulator. So the question is, how does this insulator differ from the one that we had before, diamond or gray tin or whatever it is? The answer to that question is actually resulted in the Nobel Prize in Physics in 2016. So the Nobel Prize in 2016 went to David Thouless, Duncan Haldane, and Michael Kosterlitz for theoretical discoveries of topological phase transitions and topological phases of matter. So there's an and in here. And really, this is kind of two prizes. They're a little bit distinct. And the reason we know it's two prizes is actually, if you look carefully, Thouless won half of the money, and Haldane and Kosterlitz won 1/4 of the prize money. So something is inequivalent there. And the reason is that there's this idea of topological phases of matter, which Thouless and Haldane contributed to, and topological defects and topological phase transitions, which Kosterlitz and Thouless contributed to. So Thouless was involved in both, but they're really kind of distinct, and it's really this one I'm going to talk about, this topological phases. So what's a topological phase? Well, we used to think that phases of matter were all distinct from each other due to some kind of spontaneous symmetry breaking. So if you broke a symmetry, you would get a new phase. So a crystal breaks translational symmetry, and so it's distinct, and so that's a new phase of matter. A magnet breaks rotational symmetry, so there's a particular axis along which we have a magnetization, and so that's a distinct phase. Superconductors actually turn out to break gauge symmetry, so you can distinguish them in terms of a breaking of a symmetry. And so this is an idea. It's largely due to Landau that you can think of phases as things that break symmetry. But in this quantum Hall state, there's no particular symmetry that's obviously broken. It does require a magnetic field, which breaks time reversal symmetry, but that's there throughout. So it's not really clear, what distinguishes, one of these integers for this integer 6 versus 5 versus 4, et cetera. And so the answer came from topology. And the idea is that, so this is my physicist version of topology. Topology tells us that a sphere is the same as a muffin and a coffee cup is the same as a donut. Right, that you can continuously deform a torus or a donut into a coffee mug without breaking the surface. And so that's actually a mathematically rigorous statement. And the reason is that you can take this thing called the Gaussian curvature, K, you can integrate it over a surface. It could be the sphere or it could be the muffin. And if you integrate this curvature everywhere over the surface, you'll get an integer. And that integer is 2 minus 2 times g, where g is what's called the genus. And if it's a sphere, a genus is 0, or if it's a muffin or a plate, genus is 0. And if it's a torus or a donut or a coffee mug, the genus is 1. And so smooth deformations of that surface, you know, deforming the torus into the coffee mug don't change this integral. So this G then is called a topological invariant, and it's something that doesn't change when you change the surface a small amount. So it turns out there's a topological invariant that can be defined for a band that's of a full band of electronic states. And so you can define another vector, which is this Berry connection. And if you integrate it over the entire surface of the Brillouin zone, you'll also get an integer. Well, you divide it by 2 pi, and then you get an integer. And this integer, nu, is exactly the same integer that appears in this quantized Hall effect. So it says that these phases are distinct from each other because they have a different integer nu. And that's, so it means, in fact, the conventional insulator that we knew about, where with conductivity is just 0 everywhere, has nu equals 0. And so it's one kind of insulator, but there are other kinds, and they're distinct because of this topological property. So another thing about these topological insulators is that because this topological invariant is invariant, it doesn't change. You can't make a small change in the material and change this number. That means if you actually go from a state that has one topological index, say nu equals 1, to another one, like the vacuum, which has nu equals 0, it's a regular insulator, you have to make a drastic change in between. And in fact, that drastic change is that you have to close the band gap, and you actually have to have a metal. And so another thing about topological insulators is that they always have metals on their surfaces or their edges. And in fact, it's this edge in the quantum Hall regime that is carrying the current and leads to this 0 resistance. And so in fact, the edge is a perfect conductor in the quantum Hall regime, and current can flow along this edge. It actually flows only in one direction, and that's why it's a perfect conductor, is that the electrons can't backscatter. But this is generic, that whenever you have this topological phase, you'll have something interesting that happens at the surface. Okay, so I gave you one example of a topological material, and so then the question arises: is this the only thing? So as Landau levels, there's electrons in a strong magnetic field. Is that the only topological insulator? Of course, the answer is going to be no. But the answer comes about actually in a very funny place. I told you about band insulators at the beginning, where you have this gap that arises at these special momenta at the edge of the Brillouin zone. But there are some cases where that gap actually doesn't happen. So graphene is one. Graphene is two-dimensional graphite, so it's a single layer of carbon atoms. And there, the bands actually cross at this special momentum, and you don't get a gap. And it's protected by a symmetry. That symmetry is that you have a hexagonal lattice, and you've got 2 atoms in the unit cell, and they're both carbon, and so they're both identical. So graphene looks like this. The band structure was actually worked out in 1947, so quite a long time ago. And it looks like this if you plot it. You have these 2 bands, this valence band and conduction band, but they touch at these special momenta. And around those momenta, the energy is linear in momentum. So you have something that looks like photons, E equals Cp, except here we've got a Fermi velocity, which is about 1/300th of the speed of light. But in some cases, in some sense, these act like, massless electrons. So they travel at some constant velocity independent of their energy. And in fact, they're described by something that looks like a massless Dirac equation. So pretty neat stuff. So one of the things that happened when graphene came along, whoops, yeah, there's a missing slide, but that's okay. So So actually, you know, to answer this question, are Landau levels the only system that have this this non-zero integer nu? Haldane answered this question back in 1987. So this was actually before graphene. And in fact, in this paper, in figure 1, he says, you know, the honeycomb net model 2D graphite. So people didn't know about graphene. We didn't have the word graphene. But they were thinking about it as kind of a theorist's toy model. And so what he did is he considered graphene, but he considered it with a kind of funny periodic magnetic field. So the net flux is 0, but there's some flux, you know, positive in the middle of this hexagon and negative around the edges. And so it breaks time reversal symmetry. But it obeys the lattice symmetry, and in fact, it could represent some kind of magnetic material. So you could actually be some real material. And if you do this, actually, you find that when this field is 0, you get this Dirac point. But when the field's not 0, you get a gap. And in fact, if you calculate this, this TKNN index, it turns out to be 1. And so you do get a quantized Hall conductivity, but there's no Landau levels. So there's no, you don't have this Landau level ladder. So this is something new. You know, this was kind of a theoretical curiosity for years. But then we actually got graphene. So experimentalists were able to make this, and you know, it turns out that you know, you take graphite and you smear it against any surface, you actually get a bit of graphene. You don't use pencils, but you use little, you know, crystals of graphite and put them on the right surface. Silicon dioxide on silicon is nice because it makes it easy to see. Then you can actually see single layers of graphene on the surface. And you can make little electronic devices where you put electrodes on the graphene. They're separated, you know, they're on an insulator, so you can run current through them and measure voltages and stuff like that. And these guys, Andrei Geim and Kostya Novoselov, actually got the Nobel Prize for making devices like this and then doing interesting experiments showing that they had this, this heroic electronic properties. So then that allowed people to really start thinking about graphene again. Two theorists, Charlie Kane and Jean Malie, started thinking about what perturbations there might be to graphene. So this is this graphene Hamiltonian, and they said, well, you know, maybe these atoms aren't the same. You know, maybe somehow the charge could spontaneously rearrange on the two atoms in the unit cell, and you'd get some kind of charge density wave. So if that happened, you'd get an insulator. That's what they calculated. And they also said, well, you know, maybe there's some spin orbit coupling. It's small in carbon, but, you know, it's probably there. So they put in this term, and then they calculate what happens. And they also get an insulator. And these two calculations are actually done on strips of graphene. So they have some finite width. And there's a difference between the calculation and these two insulators. And the difference is these red and green states. And those red and green states actually, in this case, cross the gap. And in this case, they don't. And that's an important distinction. And now we actually know that this case is what we call a topological insulator, and this case is what we call a trivial, conventional, regular old insulator. And the difference is that these states that cross the gap actually are states that live on the edge. And there's no magnetic field here, so there's, you know, we can't get a, you know, so that everything has to be time reversal symmetric. But we do have these states that go one way along the edge, and what they do is they carry spin up in one direction and spin down in the other. And so if you reverse time, you reverse the spin and you reverse the momentum, and this thing looks the same. And so now you've got something that's kind of like quantum Hall effect, but it requires no magnetic field at all. They were able to show there's actually only two kinds of insulators with no magnetic field. So you only get this one and the regular one. So we thought there was one kind of insulator. It turns out there's two, and this is the other one. So graphene actually turns out to have really small spin orbit coupling, so it's hard to see this state. But if you take something like mercury telluride and you make it 2D, then it has very strong spin orbit coupling, and you actually can have this state where you have a gap and then you have these edge states in the gap. And so this was done experimentally. And in fact, if you tune this Fermi energy into the gap, then with a gate voltage, you actually see that the conductance plateaus at this 2e squared over h. And that 2 comes from the fact that there are two edges carrying e squared over h conductivity perfectly without resistance from one side of the sample to the other. Another neat thing about this quantum spin Hall effect, or this topological insulator without magnetic field, is that unlike the quantum Hall effect, this can happen in 3D. So here we, in 2D, we've got a 2D bulk that's insulating and 1D edge states that conduct, that have spin and momentum that are locked to each other. But you can have 3D materials that are insulating in their bulk, and then on the surfaces, they'll have this metallic state that has spin and momentum that are locked to each other. Generically, it tends to have this Dirac dispersion, kind of like graphene. And so those materials are known as well. So they were theoretically predicted to happen in compounds like bismuth selenide and bismuth telluride. And then they were experimentally observed right about the same time. So this is an angle result photoemission spectroscopy experiment where you can see the bands, this energy versus momentum directly, and you see it's actually a conduction band up here and a valence band down here. And then this is the surface state that goes all the way through the gap, and it has this Dirac point. And so, so these things really do exist, and then they even show that these things are spin polarized, so the momentum and the spin are correlated. All right. So what does Fleet want to do? How are we going to use these things? So our idea is that we'll make a topological transistor. And so what we want to do, a transistor is a 3-terminal device. We have a source and a drain and a gate that controls the current from source to drain. So what we imagine is that we'll use a voltage on the gate to create an electric field, which will transform a material from conventional insulator, which is insulating, doesn't conduct, the topological insulator, and then it'll have these edge modes that'll conduct perfectly without resistance from source to drain. So that's our vision. This is the one slide on research. So we've been able to do this, or at least the first step in this kind of thing. So the topological insulator that we have that we're working on is actually sodium-3 bismuth. So we can make sodium-3 bismuth very thin, so it's 2D. So this is actually one layer of sodium-3 bismuth. This is 2 layers. Then we can bring an STM tip in, and we can use it actually to measure the band gap in the sodium-3 bismuth. It looks something like this. If we measure differential conductance, so the conductance from tip to sample as a function of bias voltage, that actually reflects the density of states versus energy, and it shows a gap. And so here the gap's about 300 millivolts. And then we can also use the tip to apply an electric field. And we do that actually by bringing the tip closer to the sample. It has a very different work function than the sample. And so there's a field that just depends on distance. And so as we bring it closer, actually, this band gap, you can see it actually closes down. These curves are offset for clarity. So the band gap closes down, and it closes down to a point where it seems to disappear, and then it opens up again. You're going to see, whoops, went the wrong way. Yeah, so the band gap is closing down, it vanishes, and then it actually opens up again. And so, comparing to what we expect from theory, the theoretical calculation shows us with an electric field, we expect that the band gap is topological. It closes down to 0 and actually opens up again as a conventional insulator. And again, you always have to have at the boundary between topological and conventional, you have to have a metal, and that's the gap always has to close when you transform from one to the other. So what we think we're able to do is use this scanning tunneling microscope tip to, in some sense, apply a field and undo these knots of the topological band structure of the material and convert it into an unknotted conventional insulator band structure. And in between, there's a metal. And so actually in the material, there would be in between, there'd be some metallic edge state. Okay. All right, so that's all I'm going to tell you about today, although I'm happy to take questions. I showed you just a tiny bit of our experimental work, and it's described in this paper here if you want to read more about it. And again, you know, I'm working in this Fleet Center. We have other people who are funding our work that we work with. Thanks, and I'll take questions from there.
Hi, thank you for your talk, Dr. So I have not taken solid state, but I did just take grad string theory. And I was really surprised how much, I kind of knew that there was a similarity, but seeing it in your work, it made me want to ask both, how much do you feel it's easy to go across fields and look at the math and maybe borrow or look at discoveries? And second, I heard that I couldn't find the paper, but I did hear a talk at LBL with ADS-CFT being used to describe both superconductivity with high magnetic fields and I think it was quantum chromodynamic interaction, so gluons.
Yeah.
I know that's a small niche thing, but it's
a really good question. I mean, I would say so. Actually, my understanding of ADS-CFT is not very good, so I don't want to. I'd say end up saying something wrong. I think if I tried to.
I do all the time, so don't worry about that.
But I guess what I'll say is that what condensed matter systems do, as far as I can see, or my sort of view on this, is that condensed matter systems allow us often to design interesting Hamiltonians that then allow us to see what happens and, you know, to sort of examine and play with those Hamiltonians, right? So for example, you know, if you want Majoranas, you know, Majorana particles that are their own antiparticle, well, neutrinos may or may not be Majoranas. They probably aren't. But, you know, in condensed matter, we've been able to design a particular Hamiltonian in a particular material. You know, they do it with strongly spin orbit coupled nanowires of semiconductor in a magnetic field that's oriented in the right way. And, you know, you do everything right, and you can make Majoranas. You can make electrons. Well, you know, they're not electrons anymore. They're these quasi-particles, you know, excitations of the system that actually are their own antiparticle. And so you can design a lot of things that, you know, where the effective Hamiltonian is something that, you know, might be relevant to particle physics or what have you. You know, whether you actually learn about particle physics, I'm not sure. You know, you do tend to, you often, you know, go beyond the basic Hamiltonian, you know, the basic physics, because condensed matter systems are complicated, right? You have interactions and things that are not necessarily soluble analytically, right? So once you have a bunch of different quasi-particles that can interact with each other, it's, you know, rapidly becomes a system that is complex, and these complex systems actually can have emergent behavior. You know, so superconductivity is emergent. You know, it requires interactions between electrons to generate that system, and so, you know, it's possibly not the kind of thing that you would guess would exist, you know, unless you observed it. And so I think, yeah. So anyway, you can design interesting Hamiltonians. You know, in some sense, it's easier, you know, because you have a lot of different you know, knobs that you can play with. In some sense, it's harder because, you know, you only get the materials that nature allows you to have. But it turns out that there's a lot of things that you can do with those materials, and so I think it's quite powerful to look at different physics.
Thank you. That was an excellent answer. I really appreciate it.
Sure.
Other questions?
I also have a question.
Yeah.
So this technology is super interesting. So how long, or I guess, when do you think we'll see this kind of technology in everyday devices?
Yeah. That's a tough one. I certainly get asked that a lot. my head of school, actually, it's funny. He's very realistic, almost pessimistic. And I'd say what he tells people when he talks about my work is he says, well, you know, these guys probably only have a 1% chance of being right and making something useful. But, you know, this is a $10 billion a year industry, you know, that has impacts on hundreds of billions of dollars in industry, you know, that all use computer chips, you know, sorry, it's a $100 billion a year industry. So it has impacts on, you know, trillions of dollars of industry around the world. And so, you know, if you have a 1% chance of doing something that's going to transform that industry, you know, it's a big deal. I don't know. I mean, it's a very hard problem. You know, the transistor, I mean, the field effect transistor really came out of physics, right? It came out of Bell Labs. And, you know, hopefully physics has another transistor in it that, you know, we can discover. Maybe not. Maybe there's nothing, you know, and we're going to, you know, we've gone as far as we can, and we're going to have the best computer chips that we can possibly imagine making, you know, in the next few years, and we'll just make them over and over again. I doubt it, right? I think we can do something better. You know, so, and there are a lot of different approaches that people are trying. I mean, the fun thing is that it is sort of back to basics, completely open problem. You know, there's you know, it's like quantum computing. There are a dozen different possible solutions. They're all impossible, you know. I mean, they're all, you know, if you look at them, you're like, oh, that could never be done. But, you know, physics doesn't, you know, there's no fundamental physical principle that says you can't do it. And it's just, they're all very difficult. And that's cool. I mean, it makes it an interesting research problem. I don't know how long it's going to take before we actually have a better transistor. I mean, it's definitely more than a decade.
I think that's probably about right.
Yeah, I mean, I think actually we're going to see in a couple of years, this is going to become, it's already become a little bit, you know, in the public consciousness that this is a problem, that computers are using a lot of energy and they're not going to get more efficient. And I think in a few years it's going to be even bigger deal. I don't know if you saw these stories, but when the Bitcoin bubble was happening, you know, at one point, so the Bitcoin it's based on this blockchain, and making new blocks in the blockchain is lucrative. You know, you get money for making a block, but and they had to make it hard somehow so that it would be worth money. And they made it hard just by making a computationally difficult task, right? So people said, you know, so people just went out and bought computers and put them wherever electricity was cheapest in the world to just mine, you know, these computational tasks for new blocks in the blockchain and make money. And at one point, you know, Bitcoin was using more energy than Ecuador, because just for nothing, right? I mean, basically to create these blocks, you know, to solve these hard computational problems, and it just shows you that basically computation equals energy, right? And if you want more, it costs more energy. And so anyway, I think it's going to become a problem, unfortunately, before it gets better, but you know, hopefully it'll get better.
I have a question.
Yeah.
Yeah.
Sure.
So you showed data, you showed STM, little tiny set of molecules, super cool experiment, right? So that's proof of concept. Okay, great. Now you want to go to the next level towards device in my hand, right?
Yeah.
What's as simply as you can, like, what's that next step look like?
Yeah, so that's really tough. So we have this one material that works really well in certain ways, the sodium-3 bismuth. The problem with it is that it's very reactive in air. It's mostly sodium. We take our samples out in air and they just evaporate, basically. So we do all of our experiments in ultra-high vacuum, which is, you know, it's not practical. We'd like to make little micro devices, and they really need to be kind of air stable to do that. So we are pursuing one track, which is to take this sodium-3 bismuth that we can make and kind of put some capping layer on top of it to make it stable, and then be able to try to make some little transistors. But I think it's very challenging. I think, unfortunately, the reality is that this particular material is it's very challenging. It's a great material for theorists because it's very simple, and it can, it led us to this, we were able to show first this electric field switching, but I think it's difficult, to make it practical. And so we're looking for other materials. There are some that have been proposed that can make this kind of transistor. But it's a big, I think, what we're hoping to do at the end of our center, we're about halfway through. It's a 7-year center, and we've run for 3 years. And we're hoping by the end that we'll have a transistor. So one transistor, right? That we can say, look, this thing works, and it's better than the equivalent silicon transistor, even though it's not. We haven't pushed it to that 3 nanometer size or whatever. And then that would get some interest from companies to actually do the R&D to try to make better transistors. But it's a big engineering challenge.
I have a question for you.
Yeah.
So, what is the reason you're going down the classical computing route rather than quantum computing route?
So look, quantum computing is really fascinating too. I mean, I don't want to bash quantum computing. I like to mention it just so people know that we're not trying to make a quantum computer. We don't think quantum computing is going to solve this problem. That quantum computing, it actually allows you to do certain computational tasks vastly more efficiently, right? And that's important. There are probably tasks that quantum computers can do, enormously more efficiently. But as far as we know right now, it's not every task, right? So we don't know how to use a quantum computer to do regular old computing efficiently. And it's not clear that, those efficiency gains are going to be essentially, we're going to be able to use them on a vast scale, right? And quantum computers probably still will have to be, these things that are cooled down to 100 millikelvin, which requires enormous amounts of energy. To extract a watt at 1 Kelvin requires a kilowatt at room temperature, right? So it's not really clear that's going to solve the problem. And the people doing quantum computing don't claim that they're going to solve this problem, right? But it is a problem, and like I said, I think it's interesting from a fundamental physics point of view. It's an open challenge. It's new, we know it's going to have to involve some kind of new physics, and so we get to work on this new physics, and it's important. I mean, personally, I think that's the best area to live in. Is the best area to work in is some area where the physics is really exciting and interesting, and you're doing something important, right? It just it's more fulfilling. So that's why we work on it.
So the system you showed in your slides, where you have the topological insulator sandwiched with 2 conductors, it seems like the systems that are used in quantum computing are actually really similar, except it's 2 S-wave superconductors coupled to a semiconductor in the middle, which has Majorana bound states. So it seems like you're almost going down that same kind of route, but not exactly.
Yeah, I mean, there's a connection between some of these quantum computing schemes and what we're doing. So if you want to do topological quantum computing, if you want Majoranas, you need topological superconductors. So you need to take a topological material and make it superconducting. And so there is a connection. I mean, there's an overlap in those research areas. We're not particularly pursuing those directions in our center. Part of it's just because we have a center, and it has a mission, and the Australian funding system, they really like that. They want you to have a real concrete goal with a mission, and that's what we're doing. And, you know, like I said, it's a good mission. Everybody likes it, and it's exciting to work on. Quantum computing is big in Australia as well. I mean, there are, and you know, we know so there are a couple of centers of excellence that are doing quantum computation stuff. One of them particularly in solid state, and you know, we know those folks and we collaborate with them, and so there is overlap between those kinds of you know, those areas of research for sure. Yeah.
Thank you.
Anything else you've ever wanted to ask Dr. Fuhrer? Now is your time.
Yeah, I have a question. So as an experimentalist, like this seems like, you know, pretty like cutting edge sort of theoretical stuff. So what is your relationship to the theory and the theorists, and like what does that chain look like for you between like concept and executing an experiment?
Yeah. I mean, my understanding of the theory is kind of modest. You know, I like I actually enjoy trying to take the theory and understand it enough that I can sort of tell other people what's going on, you know, and give talks like this. But that's, I mean, when it gets beyond that, I'm a little bit out of my league. I mean, you know, as an experimentalist, you definitely have to have a reasonable grasp of the theory in order to understand what you're doing. But you know, we collaborate with theory groups. You know, so I have some very close theoretical collaborators that, you know, I work well with, and I talk with them at length about, you know, what's going on, and you know, generate new ideas that way. So I think you know, I think collaboration is important. And this theory experiment collaboration is really critical in physics, especially in this field. So yeah, I mean, why we have experimentalists and theorists, I don't know. I mean, it's a cultural thing, but you know, that it seems to work, and you know, that collaboration between different people that look at problems in different ways, you know, tends to generate new ideas pretty well.
Okay. Any other questions? If
Sorry,
not,
I have one more question.
What last question? Go on,
I'm gonna
Trey.
take advantage of this opportunity, but so is it true that Majorana edge states can exist in a topological insulator, or does it require a topological superconductor?
I believe that it requires a superconductor, a topological superconductor. There, you know, basically, I mean, so the edge states in the topological insulator are still real electrons, right? And you know, there's a sort of fundamental thing that you're trying to do with to make Majoranas, is that you want to get rid of the fact that fermions are typically doubled. You know, that they come and spin up and spin down, and positive and negative momentum. And you have to kind of do that twice. And once you get sort of one for making it topological, and another one for making it a superconductor. And you know, that's basically what happens. And so I think you need both. I'm not sure that there's any Majorana scheme that doesn't kind of use these Bogoliubov quasi-particles to allow you to do it. So I think it needs to be superconducting.
All right, thank you so much.
But you know, somebody will prove me wrong. I don't know. Maybe some other way to do it. I mean, that's the cool thing about condensed matter. You can always come up with some other system that maybe does it as well. I don't know.
And Michael, I was wondering if anybody thought of any questions like tomorrow or in the shower or something next couple of days. Would it be okay if I share your email address? They could ask you.
Yeah, that's
question or
fine.
two?
Sure. Yeah, I try to respond to emails. Hopefully, I'll get back to you. Yeah.
Well,
if I don't, just email me again. It's not out of, you know, not lack of interest. So
I think that's the professional way things go during life. So round of applause for Michael Fuhrer. Great job. Super awesome talk. I learned a couple of things, so I appreciate that very much.
Good.
And thank you for this, Michael. We appreciate you. And I'll be in contact later, and we'll send you a a fancy mug of some kind so that you can drink
Oh, terrific.
caffeinated
Okay,
beverages or
thanks.
whatever.
All right. Yeah. Cool.
Okay.
Well, it was fun. I enjoyed it. Great questions, and yeah, I'm glad I could do it.
Hope you have a great rest of the, or hope you have a great day, and the rest of you a great rest of the evening, and I will see you all next time.